Shall I start?
Yeah, I think they're arriving. Okay, I think we can start, yes.
Okay, good afternoon, everyone. The lectures were on fractionalized phases of matter in 2 dimensions, which also have a gap to all excitations. And my last 2 lectures are going to be on quite a different topic. The basic theme of the subjects we covered so far is that you describe a quantum many-body system by its quasi-particle excitations. Now, in Fermi liquid theory, these excitations are just electrons or renormalized electrons with some renormalized mass and some renormalized interactions. And in the more exotic phases, these are anyons of various types with different statistics, spinons and bosons and so on, and semions. So we met, I guess, gave a gentle introduction to some of these topics and how these exotic phases can be realized. So today I want to turn to a different class of exotic phases, which at least are much more common in experiment. If you take a typical condensed matter experiment in some material, it's really hard to find a phase with a nice gap, which is not perturbed by some disorder or anything. And then you have to work very hard to look for fractionalization. There are some very nice examples now, but it's rather rare. On the other hand, if you take almost any strongly correlated material and at a generic density, then it's a metal. It has conducting electrons. It's highly gapless. There are lots of gapless excitations, no matter how you look at it. And also, there's this regime where the standard theory of metals, the theory of Fermi liquid theory and all its variations, simply doesn't apply. So if you look at the transport properties, they don't fit the predictions of Fermi liquid theory. And then if you look at photoemission or various other spectral probes, you don't see any sharp quasi-particles. And this is quite common, and invariably these strange metallic states appear in materials that at lower temperatures display some kind of ordered state, superconducting state or antiferromagnet or a charge density wave or some combination thereof. And these ordered states, when you look at them, are at least in the low energy limit rather conventional, that they fit into the paradigm of ordered states with broken symmetries and low energy quasi-particles about the broken symmetry state. But it's the higher temperature state, the parent states of these ordered states, which are the most mysterious. And this is something, it's been a problem for a while, and we really do want to understand these low temperature states, these higher temperature states, because only if once we understand them can we answer questions about the lower temperature states, about what their critical temperatures are, what the type of ordering is. All of this we can't predict ahead of time. And I think the reason is mainly because we don't understand the parent metallic state. So that's sort of what we want to do. That's been an open problem for a long time, and I'll talk about some recent ideas, especially those that built upon the Syk model in these last 2 lectures. So that's the theme, quantum matter without quasi-particles. But before we go there, let me talk about a simple model with quasi-particles. So what I'm going to do today is talk about models with random couplings. In fact, they don't even have a sense of space. They're just models, in the spirit of Parisi's spin glass model, where everything is coupled to everything else. But these are quantum models. And the models I'm going to describe don't have spin glass order. So we don't have to worry about subtleties with replica symmetry breaking and associated phenomena of non-self-averaging. We can just work in the replica diagonal limit and everything in the large n limit with the number of sites goes to infinity just self-averages. So there is some simplicity there, the disorder is present, but it doesn't really show up in any fundamental way in the states we'll talk about. So then you can ask legitimately, why do we introduce disorder? Well, somewhat paradoxically, it makes life simple. It allows you to solve a problem in a strongly interacting regime that without disorder, you would have no hope of solving, and even get some exact results. And furthermore, you can also do numerical studies and check some of the analytic ideas, and even go to regimes where the analytic solution doesn't work. And in numerical studies, even though they're relatively small systems, since you know the system self-averages, you can just take many, many samples. And that way, you seem to approach the thermodynamic limit much more rapidly than you can with systems without disorder. So these are all various reasons why looking at disordered system is valuable. I mean, that's just been my experience, and it seems to have paid off to some level. But anyway, so today we'll be mostly about disordered systems. In fact, all about disordered systems. But tomorrow in my last lecture, I will say some things about systems without spatial disorder. But there also, some of the lessons we've learned will be very useful. Okay, so let's just begin with a simple model with quasi-particles and also with disorder. So what's the idea of systems with quasi-particles? The main idea. So the idea, roughly speaking, is you have some quasi-particle excitation. These are simple excitations above the ground state. And they have a bunch of energies E alpha. And this the alpha, it can be very large. It's just proportional to the number of sites or the volume of the system. That's the number of labels you have to label these quasi-particles. So these are simple particle excitations above the ground state. But there is a much more fundamental assumption, which is that you can take a many-body excitation, of which there's an exponentially large number of, for e to the n. You can take a many-body excitations and just think of it as a superposition of lots of these quasi-particles. Now, the quasi-particles do feel each other, but that, that doesn't fundamentally alter the fact that you are describing a many-body state as a combination of simple single particle excitations which are very small in number compared to the exponential size of the many-body Hilbert space. So typically what you introduce is a quasi-particle distribution function. Say f of E alpha, the number of quasi-particles pulling unit volume or something with energy E alpha. And this can be renormalized by the presence of other quasi-particles. So the actual energy that goes in here would be some bare quasi-particle energy. So let's call this 0. We just have a single quasi-particle. Plus some interaction, some on beta, some interaction parameter, which is often called the Landau parameter, and the distribution of all the other particles. So this becomes some kind of self-consistent equation or Hartree-Fock type equation to find these quasi-particle energies. And once you have them, even in the presence of external perturbation, you can just treat them mostly independent of each other. However, they're not entirely independent. They do collide. And eventually, their integrity disappears. So you do get some very complicated chaotic many-body state, which has somehow reached thermal equilibrium. But you can describe that process perturbatively. And it was really Boltzmann who showed how that happens for a classical gas. And the Boltzmann equation pretty much continues to apply also for the quantum, for this kind of quantum quasi-particle description. So you have the collision term in the Boltzmann equation, and that will give you some quasi-particle collision rate. Or more simply, in the quantum case, you can also use Fermi's golden rule to estimate the collision rate. And when you do this, there's a self-consistency condition that demands that this collision rate be small enough. Because if it's not very small, then this whole process of thinking of the many-body state as just a superposition of single particle states is not self-consistent. And so you have a typical requirement that the lifetime of the quasi-particle or the collision rate of quasi-particle be much, much smaller than the quasi-particle energy. And as long as this is the case, then the quasi-particle description works. So in a Fermi liquid, this first state I'll talk about, this quantity tends to be about a temperature squared. And this, typical energy is about a temperature. So at low enough temperature, this is always satisfied. And this whole picture works. Okay. All right. So what we're going to be interested in, our system where this picture doesn't work. And then you're at a loss as to how do you describe a given experiment. And what you often do is you try to take this picture and force it on the system where it shouldn't work. And when you force this description on a non-quasi-particle system, what you will find is that this time it basically becomes about a temperature. So this is for non-quasi-particles. Okay. So, however, then, so this inequality is violated. And even the sense of interpreting as a quasi-particle relaxation time doesn't make sense. So you have to think of other ways of defining some coherence time or whatever of your quasi-particle excitation. So you can look at the widths of certain spectral functions. And these days, especially coming from connections to quantum gravity, there's been the idea, very beautiful idea of looking at time autocorrelation function to characterize this collision time, or as they say at the time, to many-body quantum chaos. And when you come up with more precise definitions, what you often find is that this time, it has the same units as temperature. Once you convert temperature to a time as a frequency with kT to nh bar. And once you define it carefully, this number here becomes a pure number. It turns out to be independent of all kinds of microscopic details. And in some cases, it's a universal number whose value, of course, would depend on precisely how you defined it. So for example, if you define it using the OTOC, then there'll be a precise coefficient you can put here. Anyway, okay. So these are the type of properties you want to see in some non-quasi-particle system. And as I'll discuss today, the SYK model is one such system where you can compute all of these things very precisely. Okay. All right, so that's about introduction, and hopefully most of it familiar to you before. So let's now talk about a very simple model, which will just set the stage for the SYK model, where you do have quasi-particles. And this is the random matrix model. So the Hamiltonian, I'll take spinless fermions, is -1 over square root of n, sum on I less than j, Tij, T dagger I C j, and you also take the chemical potential. Okay, so here I and j go from 1 through n. And these are just spinless fermion operators. And these matrix elements couple every site to every other site, just like in the Anderson spin glass model. But you take this to be a random matrix. So Tij are independent random variables. The most important point is that they're independent. independent random variables, and have some second moment, which is we call t squared. Okay, so this is, I've written it as a many-body problem because that's to get us ready for the many-body aspects we'll talk about later. But it's really a single particle problem. All you have to do is diagonalize an n by n random matrix, for which there's books have been written on that problem, and you get some distribution of eigenvalues. In this case, in this ensemble, you get a semicircular density of states, which I'm going to derive in a few minutes. And there's also a lot of work on the spacing between the eigenvalues and their distributions. This the Wigner-Dyson theories, which I won't really need for anything I want to talk about. Okay, so now once you have the eigenvalues of this matrix, then you can go ahead and occupy, will be a very low temperature. You'll occupy this the state. So I'm going to introduce a quantity I'm going to call Q, which is 1 over n, some I. So that's the density, which I'm going to call Q. So Q is the density, and we go between 0 and 1. Because if all states are occupied, then it's 1. If they're all empty, it's 0. And that depends on the value of mu. So mu and Q are just related to each other through some the usual relation between chemical potential and density. Okay, so let's just go ahead and determine the density of states. That's very easy to determine, especially when you take a many-body point of view. So we define a Green's function, Gij, which will be minus the time-ordered product of C to I of tau, C dagger of 0. As usual, at site J. And we'll try to determine this by in this for this Hamiltonian. Now, of course, if I give you a set of Tij, it's hopeless. But what you can do is put the Tij on a computer and get the eigenstates and the eigenenergies and determine Gij. So we'll be interested in the behavior as n goes to infinity. And to begin with, I'm just going to average the Green's function. I'm going to average over the Tij, and I'm just going to do it perturbatively in powers of t. Now, in principle, that doesn't mean it's the exact answer. If you did this for the spin glass problem, you'll get totally the wrong answer, even though there's a well-defined large n limit, which Parisi discovered using replica symmetry breaking. But here it works. It works because this problem is self-averaging. There's no spin glass, it's just free fermions. Okay, so if you just do perturbation theory, there'll be a bare Green's function, plus there'll be from site, well, you start from site I, there's a factor of t here, and then, sorry, j over there. And two of them, t, and sorry, j, and so on. These are the graphs in perturbation theory. I forgot to mention here, so this is the average over samples. I also forgot to mention it's convenient to take the average of Tij to be 0. If it isn't, you just shift it and absorb it in the chemical potential. So not a big deal. Okay. So, right. So now I'm going to take the average of each graph. So this one will give me 0 right away. So this is 0. But this will not be 0 because it's got because of this. And the way I represent, and this has to be the symbols have to be the same. So this is site I, and this is site K, and that's J. And you average this, you represent this by that. So this is IK, well, that has to be KI. So J must equal to I. So this thing, when the dust settles and you average, this thing is going to equal G0. Well, I should first say what's G0. So G0 is this term here, which is G0, which is I omega minus mu or plus mu tan delta ij. This is the delta ij here. So there will be a G0, then there'll be a factor of t squared, another factor of G0 from here, and a G0 over there. And a delta ij again. So this graph also gives you only a diagonal contribution. There's a sum over k, but the point is the sum over k goes over n values. You get a factor of 1 over n from here, and you sum over k, and that cancels the 1 over n, and so there's no factor of n. And in fact, that's the reason we put the 1 over square root n to begin with, so that this term would come out to be about a 1. All right. And now you keep going. So that's the first term. Then if you go to third order, of course, it's all 0. And at fourth order, there's something interesting that happens. There's a variety of terms that can contribute. And okay. So at fourth order, you get terms like this. You get this. You'll get this. And you'll get this one. Okay. So you can put in all the indices and do the average, and what you find, and I won't write it out, this will be about a 1, this will be about a 1, and this will be suppressed by some power of n, and I think it's 1 over n. Okay. So this particular graph you could throw out. And doesn't contribute as n goes to infinity, and so on. So you do this to all orders, and what you find is that it's only graphs of this type, where the lines don't intersect, that contribute. So you can actually combine all of this into a very simple set of Dyson equations. So you can write your G of omega is equal to I omega. Is I omega plus mu minus some self-energy of I omega. And the self-energy is basically t squared times the full Green's function I of omega. So these two equations encapsulate the sum of all possible graphs of this type. So the self-energy should be a full Green's function. That's because when I make the self-energy a full Green's function, this is automatically included by just replacing one of the G naughts with the G. And this is just the Dyson contribution happening over and over again. And that's all that contributes, and then goes to infinity, and therefore you're done. All right. So this equation is quite easy to solve. It's just a quadratic equation. And when you solve it, you get a nice looking density of states. So what you then find is that the solution looks something like this. Just a solution of the quadratic equation. Then you find that G in the complex frequency plane is given by d omega pi omega, and okay, omega minus z, and rho of omega is the famous semicircular density of state. Is 1 over, it's a real function, 4 pi of 2 pi t squared, that's square root of 4t squared minus. Okay. All right, so that's the famous semicircular density of states. So let me just make a picture of it. I'll do it right here. Yeah, so omega, and this goes from -2t to t. 2t. This is omega. I'm sorry, I think I forgot a mu somewhere. So this should be omega plus mu. So you're going to fix a chemical potential, say somewhere here. And you're going to occupy these states and not occupy those states. And in fact, the states, the eigenvalues for finite n are a discrete set of eigenvalues at some random positions. But because this is because of eigenvalue repulsion, they're almost equally spaced, but not quite. There's some distribution, of course, but they very rarely approach each other. And the typical width spacing is 1 over n. So there are n eigenvalues, spacing 1 over n, and so the bandwidth is about 1. Okay, so these states will be occupied, determined by the chemical potential. Okay. All right, so once you have the Green's function, you can compute various things. So just like in Fermi liquid theory, you can compute the entropy. You can compute the free energy and the entropy. So I will spare you all the details. Some of the this is just completely standard. And what do you find then? That the entropy, the many-body entropy, S is equal to gamma times T. And gamma is the sum of a gamma coefficient, is given by pi squared over 3 times the density of state at the chemical potential. So this value right here. So that appears in this gamma coefficient, it gives you the density of states. Okay. You can also look at the energy of the system, the total energy. This is really the grand energy because I'm working the grand canonical ensemble. It'll be, some energy will be E naught, and okay, I hope I get all the factors right. So the entropy is gamma T, well, the free energy. Okay, I may get some of the factors wrong. So the energy of the E naught, I believe, so minus gamma T squared over 2, if I remember right. Sorry. And so this is the entropy. Sorry, I should also put the factors of n. S is n gamma T, and there's also a factor of n here. Okay. So it's often useful to go to the microcanonical ensemble. So you just convert these two, and you can get rid of the temperature in favor of the energy. And so if you get all the factors right, you find the S as a function of energy is square root of 2n gamma times E minus E naught. So this is a form that will be very useful when we look at other systems. Anyway, so that's just the pre-Fermi behavior of this random matrix model in the thermodynamic limit. The entropy is proportional to n here because this is of order n, and the energy is also of order n. And this gamma coefficient is the one quantity that depends on the microscopic density of states. Okay. All right, so what I'm going to do now is show you a few pictures, and then we'll go to the SYK model, where I'll show you some pictures for the SYK model and how they differ, and then we'll go back and think about how, explain how some of the properties of the SYK model. All right, so I'm going to transfer to my computer here, and I hope you can still hear me. Can you hear me okay from this place?
Yes, we can hear you.
Perfect.
Right. So now I'm going to share my screen and show you a few slides, say for about the next 5 minutes. All right, so I hope you can see the picture now.
Yes, we see.
Okay, good. Can you see my arrow also? Yes.
Yeah.
Okay, great. All right, so this is the model I've been talking about. And there's the picture of the density of states that I just showed you. I guess I called it rho 0. Okay. All right. So Now, what I want to do is to take this model and think of it as a many-body system. So what we're doing here is you look at the set of all possible many-body states. And what are the set of all possible many-body states? Well, there's 2 to the n of them. I'm ignoring conservation of particle number here. There's 2 to the n of them. So these integer n alpha can be either 0 or 1. And E alpha are these n eigenvalues right here. Say I know all of them. The chemical potential has been absorbed in the definition of E alpha. So the zero energy E alpha is exactly at the chemical potential. That's actually quite important. All right, so what's the lowest energy state? The lowest energy state will be you occupy the yellow region because you occupy, so N alpha is 1 for the yellow region and N alpha is 0 above this point. So that would be the state down here. And this is, a histogram of all possible 2 to the n states. I forget for what was n here. You can easily make n really huge because all you have to do is diagonalize an n by n matrix. And this is what you get. So this is the density of states. And this expression I put on the board. And here also I've subtracted E naught in the definition of E. Okay, so you compute this quantity. And so what thermodynamics tells us that it should have this dependence on E, and that's the behavior over here. So it's exponentially large when E is of order n, and this gives you the density of states, just a simple quasi-particles. Okay, now what we're going to do is to zoom in at very low energies and look at the very low energy excited states. What are those states? Well, those states are simply associated with these levels right here. They have nothing to do with the bottom of the band, which is off way back there. So now what you're doing is, these are the important states in any Fermi liquid theory. So you're taking particles, you're adding particles just above the Fermi level or removing particles just below the Fermi level. Those are the low energy states. And when you do that and you zoom in, what you see is this, the density of states has a tail here, becomes quite small. This is really zoom in at the bottom. And you zoom in even further at the very bottom, and you see the discrete levels. And what you see is at the very bottom, the levels are really much farther apart than they're in the middle. And why is that? Well, if you just think about the first few states, how do you make them? Well, as I just said, you make them by adding particles here or removing particles there. And anytime you do such a thing, it's going to cost you energy about a 1 over n. That's the space. These are quite large space on this spacing. So the spacing here is about an e to the minus n, because the density of states is about an e to the n, when the energy is about n. Another way to see that is that the total number of states is 2 to the n, and the bandwidth is n. So the density of states has to be about an e to the minus n. The spacing has to be very, very small in most of the spectrum, but near the bottom of the band, it's much larger. And so this large spacing, we expect, actually is very robust, will also survive the introduction of interactions. And this is, at least in this model, this is very clear evidence, if you did it with interactions, for the existence of quasi-particles. You add and remove a few quasi-particles, there's only n of them, and you'll get a much lower density of states. And why are these states so close to each other here? Well, that's because one state has no relationship to the next one. One state has a quasi-particle 5, 7, 10 occupied, the other one has quasi-particle 2, 8, 15 occupied, and they just accidentally have to be close to each other simply because there's so many of them. That's all. Whereas here, the states are the bottom states are very much related to each other. This has all the yellow states occupied. This has maybe just one extra state occupied or one particle hole excitation or something. So all of these states are very similar to each other, whereas up here, the states are totally different from each other. Okay, all right, so I spent a lot of time on a very trivial model, but let's now look at the same behavior in the SYK model, which has the same structure as the random matrix model, except you have 4 Fermi operators. So you have n orbitals the fermions can occupy. And yes. Is there a question? Okay, so I'll proceed. So here's the Hamiltonian. The U alpha beta gamma delta have zero mean and mean square value U squared. So this is a much more complicated model. If I gave you some set of U's and asked you to solve it, you would have to diagonalize 2 to the n by 2 to the n matrix. And for n above 25 or something, that's totally impossible, even by the best computers. So it's not something we can study very easily. And if I gave you a particular set of them, it's hard to tell what's going to happen. But in the large n limit, it turns out we can tell what happens when I just tell you that the U alpha beta gamma are independent random numbers. And the point is really, I don't even need an ensemble. I just need one set of random numbers. And if I look at any local Green's function on any site, it'll be the same for every member of the ensemble. So it self-averages. That's something we know from numerical studies and also for some analytical work. But it's ultimately associated with the fact that this system doesn't have any replica symmetry breaking. And the reason it doesn't have it is because the operators here, which carry the random indices, are fermions. And fermions can't condense. And so that prevents, in this particular model, Spin-Glass order from appearing. The older model from '93 is a slightly different model, although it has the same large n equations. And that, in fact, can have replica symmetry breaking in, but I won't go into that. But in the limit that we studied in '93, it's essentially identical to this model, except when you go to finite m, there's a different parameter m here, and there are some differences in the behavior. Okay, but I'm going to stick to this model, which, as far as we can tell, is totally stable down to the very lowest energies. All right, so first let me just show you some numerics over, I think this is a system of size 16 or 20 or something like that, done by Grisha Tarnopolsky. So I plot exactly the same things I plotted for the random matrix model. So here's all the energy levels and the density of states. So first thing you immediately notice, there's no tail. It's much more, compact. There's no very low energy tail, and that seems to suggest that the density of states is order e to the n up to almost the very bottom, and that's really the unique feature of this model. So if you look at it at some energy in between, first of all, you find the square root of 2n gamma e in exactly the same way as you found for this model here. Now this gamma here was related to the density of states at the Fermi level, and I don't think I'll get to that, but the gamma here is ultimately related to a coupling in quantum gravity. It's related to the Schwarzschild coefficient of the Schwarzschild. But also, so that's the same. But you also find that there's an offset of order, which is n times s naught. And then if you do the conversion from canonical to grand canonical ensemble, this offset implies that the entropy, as temperature goes to 0, has a non-zero value, s naught. Okay, and in fact, Antoine Georges and Olivier Poquelet and I computed this back in 2001, and for this particular model, it's this very precise number that you can get. Okay, so this is when you connect this to black hole problem, this is like the zero temperature entropy of an extreme black hole. Okay. All right. So, but what does this? So it's fine. I mean, there's this offset here at higher energies, but does that mean there's a ground state degeneracy? And it absolutely does not. And in fact, there is no ground state degeneracy. You can just look at the spectrum at the bottom, and here's the actual energy levels, and here are the individual energy levels. And what you find, there's no degeneracy at all. It's not like other models of zero temperature entropy, like the ice model of Pauling or various other frustrated classical models. That entropy is highly fine-tuned and it immediately disappears upon any perturbation. Here, there is no ground state entropy. In fact, what you have is that the exponential suppression of energy level, exponential spacing of energy levels survives all the way down, it seems, even at energies of order 1 over n. Okay, that's at least the conjecture from some calculations that I'll roughly outline. Okay, so there seems to be exponentially small spacing all the way down to the ground state. And that's really quite remarkable because this tells you immediately for this system that there's no quasi-particle decomposition. Because there's just not, so if you took a window of order 1 over n here, there's of order e to the n states. And you just don't have that many quasi-particles. In a window of order 1 over n in this system, you have like 5 states or something, order 1 states. And here in a window of order 1 over n, you have e to the n states, which is ridiculously large. There's just no way there are enough quasi-particle available to describe so many states. So these are really, it's in some sense the chaos between one state to the next, being totally different, here persist all the way down to the ground state. And that's the special feature of this zero-dimensional model without quasi-particles. Okay. In fact, a lot more is known about exactly how the density states behave down here. I won't go through the calculation. This comes from a calculation, I guess, originally by Alton et al. And also by Witten and Stanford. There's this e to the ns naught factor here, and there's a square root of EH. So this edge is here is square root of E, and that's somehow related to the square root of EH for the this square root of EH, which just came from a random matrix. But here, this is a random matrix. If you want to think of it as an effective random matrix, which is what Schatz, Stanford, and Stanford are now discussing, it's a random matrix of size e to the n by e to the n, not of size n by n. Okay. All right, so I think that's really right. And this is actually the complete result interpolating between these two values that you get from a quantum gravity calculation. All right. Okay. All right. So I think that's really all I want to show you. Now I'll go back to the board. Okay. All right. So yes, any questions? It's a good time to pause, actually.
Can you hear me?
So for the SYK model, that there would be too many like energy levels and for too few quasi-particles. How do I know how many quasi-particles?
I'm sorry, I can't hear you very well.
Sorry. How do I know how many quasi-particles do I have in the system?
Well, I mean, a quasi-particle, we think of it as a single particle excitation. So, for example, if I have if I didn't have this order, and then I have some particle, say even some anion, it'll have some momentum label, it'll have some spin label. Well, the spin labels will be of order 1. The momentum label on a finite system of size L will have, 1 over L cubed values or something, or 1 over some power of the volume. So the total number of labels, the total number of quasi-particle states available to me, is about the volume or some power of the volume at most. It's not exponential in the volume. That's the big difference. So if you need exponentially many quasi-particles, then it doesn't really pay to think of them as quasi-particles because there's really many body states. And how do I think of these many body states? Well, that's a good question. I don't know. We'd love to find a better way to think about what these states are. Gravity seems to provide some effective description of the dynamics of such states. But maybe there's other ways of thinking about it. That's a very interesting question for further study, I believe.
Can I have a question?
Oh, please go ahead.
Go ahead.
Okay. While you were talking about the second situation where you had the exponential scaling right down to the bottom, you went back a few slides and mentioned that square root E behavior has something to do with the bottom of the Wigner-Dyson distribution, the square root E on that edge. But I mean, it's deep in the, so that would be a filled state, whether it's an interacting situation or not, right? So why would that come up in the...
So absolutely. So that was, you're absolutely right. I shouldn't make that connection. It's nothing to do with the filled states of the single particle problem, nothing whatsoever. But in the single particle problem, we had a random matrix of n size n by n, where every entry was random. And a random matrix, quite generically, any n by n random matrix where every entry is random, has a square root edge at the bottom of the spectrum as n goes to infinity.
Okay.
Okay. Now the SYK model is a model on many body space. So it's a matrix of order e to the n by e to the n. And the number of random numbers in the Hamiltonian is not e to the n. It's of order n to the 4, much, much smaller. So it's a highly correlated matrix with most of the entries being empty. Okay, R0. Okay. Now, so that's the problem we're solving. It's some very sparse matrix with very few random numbers compared to the size of the matrix. Now you can ask, what does this matrix look like at very eigenvalues? This matrix look like at very low energies? Well, there's a conjecture, I guess more than a conjecture. There's really a lot of evidence by Syk, Shankar, and Stratford that even for the sparse SYK matrix at very low energies, you can model it by a fully random matrix of size e to the n by e to the n.
Okay.
So they propose a certain ensemble, and this came from connection to JT gravity and looking at various e to the minus n corrections there. So they have argued that even the SYK model, even though it's far from a random matrix, if you look at the many body states near the bottom of the band, you can model it by this random matrix ensemble, which has a, it's not just Gaussian, it's somewhat more complicated than just Gaussian random matrix. But that does have the square root of E edge. And that's one piece of evidence in favor of their proposal. They have actually much more evidence for it.
Okay. Thank you.
Can I ask a question as well?
Yes.
So my question is that on the first model, we saw a quasi-particle spectrum on the bottom of the spectrum. And it makes sense to me because I look at the Hamiltonian and see it's local, and basically the Hamiltonian is a band matrix. And for me, when I looked at the spectral band matrices, there's always a quasi-particle spectrum at the edges of the spectrum. And
right. So of course, it's not a very deep statement because it's free fermion. You're absolutely right. Yeah, but go on.
What I don't see is that the second Hamiltonian locality is intact, I believe, and therefore they should be, in some sense, also band matrices. And why can't I see? So the somehow I'm wrong. I know I'm wrong somewhere. I don't know where.
Yeah, well, because it doesn't have any single particle hopping. Suppose I look at this more general model where I have both the T and the U's. Okay, so suppose I look at this model. So this model, there's the band, as you say, of some quasi-particles, and there's some interactions. And this is much more, of the type of models that we like to work with. And this can also be solved for any ratio of U over T. You have to solve it numerically, and a lot is known about it. But let's just do it perturbatively in U. Suppose U is small. And in fact, that gives you the correct answer for this model. So you do perturbation theory in U, and the way you do perturbation theory is used exactly by the Boltzmann or Fermi's golden rule type arguments. And you will find that this system still does have quasi-particles. So So my claim is that, and I mentioned this very briefly, let me share again. Glasses. So my claim is that if you took the model I wrote on the board,
Yes.
this is the picture for u equals 0. But if I put in a small u in addition to the t, this picture wouldn't change. I mean, of course, the levels will move around, but you would still get this window at low energies where the spacing is about 1 over n. So in that sense, it's robust. It's actually the quasi-particles will be present even when you have interactions. And that's a much more non-trivial statement. We know we have some evidence for it. I don't have any numerical evidence, but there's a lot of analytical work that suggests that's the case. It's only when you put t equal to 0, you don't have any free particle hopping, you only have interactions, period. Then you get the total breakdown of the quasi-particle picture. Now, so that from this point of view, this may seem rather artificial, where you throw away the t but keep a u. Yeah, and for the SYK model, it is kind of artificial. And it's probably the reason I didn't think of it back in '93. It just didn't seem like a reasonable thing to do. But in the context of the spin models we're working on, this was actually very natural to have only the interaction term.
Okay.
Yeah. Right. So, but this has turned out to be, it's a very useful limit to study because it gives you a controlled model without quasi-particles. You can also study numerically and so on and so forth. And from the graph, and when you do the dual gravity mappings, this term is not very natural there. You can argue, it doesn't make sense to include it. If you do include it, the black hole just disappears, basically. Okay. There's also been work on that. This kind of induces wormholes between two black holes and so on.
One follow-up question to what you mentioned. So you mentioned that when I set the scale of Tij to 0 and only have interactions, that's only when I have this exponential crowding at the bottom. Yes, but if correct. I say switch on T perturbatively, would this still survive or it will go away? So right now I'm thinking of very large U.
So it turns out there's this energy scale, there's an emergent energy scale, and we call it the coherence energy scale, which turns out to be T squared over U. So when T is much, much smaller than U, then there's this coherence scale, and below the scale, quasi-particles will reemerge. Above the scale, you will see the non-Fermi liquid behavior, which is also quite nice as far as experiments are concerned, because as I said at the beginning of the lecture, you see this strange metal over a wide intermediate temperature regime, but eventually at low temperatures, something else happens, and that's what happens in this model too. So.
Right. So this scale looks like a second order correction, like what you would get as an energy scale of a second order correction if I look at T as a perturbation. I mean, in a sense.
The fact that it's T squared over U is actually highly non-trivial. I haven't told you enough to guess that.
No, I don't know. I just looking at it, I just made a naive guess. I'm wrong.
No. It looks trivial, but it's not. To get the fact that it's T squared over U, you have to do some analysis. Involving the scaling dimensions of the T equals 0 limit. So you have to study the T equals 0 limit, look at the scaling dimension of this operator, which you compute after some work, it's some rational number, and from that you get the scale.
Okay, so it's non-trivial.
But it's not totally trivial. It's not something you can just see without doing some calculations.
Okay, thanks a lot.
And it's also kind of nice because naively you would think the coherence energy should be just T. But it actually is much smaller than T. So, and in some sense, this is the analog of some kind of deconfinement to confinement transition, which you also sometimes see in quantum gravity. Okay. All right, so I have to stop sharing. Actually, it's time for the break then. Maybe a good time to break.
Hi, may I ask a question? A very quick question. So like in non-formal liquids, people always say the absence of quasi-particle is because they are too short-lived, right? As you also mentioned, that the lifetime is very small compared to, let's say, the thermal temperature.
Yeah.
But you also, but in the above, you assorted to the level, the spacings between levels, the density of state argument. But that's compared to the order of magnitude of n. But
Well, what
I want to ask you is,
the features of this zero temperature entropy are rather special to this zero-dimensional model. Tomorrow we'll talk about another model, much more realistic, which has no quasi-particles, which does not have this feature that the entropy is finite at zero temperature, and there's these very closely spaced levels. In fact, yeah, so that is special to the zero-dimensional limit. So it's a sufficient, so once you find a zero temperature entropy with all these states without any degeneracy, that's a sufficient condition for a non-existence of quasi-particles, but it's not a necessary condition. So that's just one comment. And it doesn't happen always, but here it's there, and so we can use it. And it's a solvable model, so that it's probably why this model is so simple and solvable, because there's all these features that allow us to really get direct access to the non-quasi-particle states, even at low energies. In other models, it's a little more difficult. You have to do some, like you said, you have to have some high energy scale where there are quasi-particles, but low energies, they disappear. That's more typical of what you have to do, but you don't seem to have to do it here. And that's a simplification that we're just getting some benefit from. Yeah, I mean, it doesn't look like this particular model that you ever see quasi-particles any energy. It just looks, even at high temperatures, it's something else. I mean, some very incoherent dynamics. But it's that incoherent dynamics goes all the way down to low temperatures. But if you had some other models, say kind of critical point in higher dimensions, depending on the parameters, there may be a regime where there are quasi-particles at high energies, but not in the Syk model. Okay, so the model we're looking at and I will be very schematic on the board. Again, the notes have much better notation and consistency and so on. Okay. So should I start? Also, I remind you, I have to end, sorry, because there's another meeting in this room. I have to end in 45 minutes, including questions. Tomorrow I'll have, we can have a discussion session after the lecture, after 5 p.m. So should I start, Andrea? Okay. Should I start somebody? Well, yeah, it is about not yet 5 minutes. I'll wait.
If you're waiting, could you just say again what happens at the scale t squared over mu that you mentioned at the end?
T squared over u, not mu. Yeah. Yeah, well, it's a crossover. It's some crossover, and you can get a crossover function numerically. And it's a crossover from where the, well, if you look, for example, at the entropy, and you can look at other things too. So if you look at the entropy, well, in the Syk model, it's coming down to some zero temperature value, which is n times S naught. But there's a scale here, t squared over u. So at this scale, it comes down linearly to 0. There's nothing sharp about it. It's you can get the whole function numerically. It comes down to 0. And so now here, the entropy is some S is, let me call it gamma star times T. But the gamma star is very large. So gamma star is about a U over T squared. This is so you can get a huge enhancement of the entropy, which is what you see more typically in experiments. You see and the effective mass of the quasi-particles become very large, and the density of states is very large. And here in this model, the large density of states and the high slope of this has to do with this low energy scale where the quasi-particles reemerge. So there's no phase transition here. It's just a crossover from, if you wish, some kind of chaotic behavior to more less chaotic behavior down here. So,
maybe we can restart this.
Okay, all right. Okay, so let me first, so now what I want to do with this SYK model is solve it like I solve the random matrix model. And so first let me just show you how you solve it perturbatively. And then I'll set up a non-perturbative formalism, which will show the connections to various quantities in quantum gravity, and that's probably when I'll have to end. Okay, so but first let's just do this perturbatively. So just do perturbation theory in U in exactly the same way as for the random matrix model, you did perturbation theory in T. So just look at graphs. So the first graph is of course just this. And for the same reason, because average of U is 0, you got to go to order U squared. So at order U squared, you'll have a graph like this. Here's U, and then another U over here. You can look at this so-called melon graph. Okay. And then at order U squared, there are also other graphs, but they turn out to be not as interesting, things like this. Maybe here. Things like that, and cubes and so on. So now there are more indices floating around. It's a little tricky, but in principle, it's almost exactly what we did for the random matrix model. So you have some indices here, alpha, beta, gamma, delta. And so when you average, these indices all have to be the same. So this will be beta, gamma, delta, and that'll be alpha. So this is a completely diagonal contribution. And there's 1 over n to the 3/2 here. So that gives you a factor of 1 over n cubed. And there's sum over alpha, beta, gamma, delta have to be summed over of 1. And that just gives you 1. So the n's disappear, and that's why you put the n to the 3/2 over here. And you try to do the same thing over here, and you will find it's of order 1 over n or something like that. And so on. And now you go to higher orders, you find almost all the graphs vanish as n goes to infinity. And there's only a small set of graphs left over. And those graphs all have this basic structure. All you have to do is replace every one of these lines by a full Green's function. And that's it. So you put it all together, and then you get the basic set of equations that you have to solve. So the Green's function is diagonal in indices. So G of I omega, if you want G alpha beta, is delta alpha beta, or I omega plus mu minus sigma of I omega. And then this graph, which is actually easier to write in the time domain, sigma of tau is minus u squared times g squared of tau, g of minus tau. Okay. So these are the, I guess I can call them the SY equations, which we wrote down for the SY model in 92. And this is it. This is the sigma is just G cubed, and there's nothing else. So now these equations are, orders of magnitude more complicated than the equation for the random matrix model, because these are nonlinear equations. And also you have to go for, it's not like a quartic equation, because you also have to go from the frequency space to time space. So there are some kind of nonlinear integral differential equations that you have to solve. It's not even clear there are any solutions. When we first wrote down, it wasn't at all clear this meant anything. So you have to try to guess and look for solutions. And then ultimately you have to do some numerical analysis to see if the solutions are actual solutions of this equations at all frequencies and time. So there's just one free parameter here, which is the chemical potential, and you're going to hope that you find solutions for some range of chemical potential. Okay. All right, and I think today we understand a lot about the structure of the solutions, but there's still no exact solution. And there's a lot of subtleties hiding in here, including effects of what's called the Schwarzschild mode, if you want to get the full frequency dependence of the solution, which is then connected to quantum gravity fluctuations near a black hole. So it's hard to imagine that these equations know about quantum gravity, but they do. Okay. All right, so how do we solve them? Well, you can't, as I said, but you can make a few guesses. The first guess you can try to make, which is, do these solutions, do they have a gap? It's some many-body state. Is there a gap above the ground state, or is it gapless? Are they excitation with arbitrary low energy? And it's easy to see that they must be gapless. There can't be any consistent gapful solutions. And the reason is the following. So suppose G has a gap delta at 0 temperature. Then you just look at this equation. And I'm going to assume the gap is the same for particle and hole-like excitations. So the tau and minus tau don't matter. So then if you're creating here you're creating 3 particles. Well, I'm calling them particles with in quotes. It's some excitation with energy. To create an excitation here, you need minimum energy delta for a single G. So here you're creating 3 of such excitations. So that tells you that the gap, the second equation tells you that sigma has a gap of 3 delta. But now you go back to the first equation, you run up to contradiction, because if sigma has a gap 3 delta, that tells you G has a gap of 3 delta, because the imaginary part of G is only given by the imaginary part of sigma. Okay, on real frequency. Okay, so this is a contradiction. So the only solution, well, actually it's not a contradiction. This implies delta equals 0. There's no other solution. Okay, so if delta is 0, what's the other? So that means a gapless solution. So let's just assume that there's some kind of a branch cut singularity at 0 frequency. And so this will tell you G of tau has some decay 1 over tau to the alpha at long times. Again, for now, I'm going to assume particle hole symmetry. That corresponds to the case mu equals 0. So just assume, take mu equals 0 for now. Okay, so this is the behavior of G of tau as tau goes to infinity. Then from the second equation, well, I can immediately say, of course, let me just say that G of omega then, well, that depends on the value of alpha. So let's assume alpha has a certain range, so that when I take the Fourier transform, this goes as so d tau over tau is the omega to the alpha minus 1. So for this to be true as omega goes to 0, I want, first of all, I want alpha to be positive, and I want to be less than 1. So 0 is less than alpha is less than 1. Okay, if it isn't less than 1, there'll be a constant here, but this will be the non-relative contribution. Okay. All right, so if I make this assumption and I put it in here, that tells me sigma of tau goes as 1 over tau to the 3 alpha. So now I take a Fourier transform in exactly the same way. Then sigma of omega will go as some say sigma of 0 plus some constant times omega to the 3 alpha minus 1. And here I'm assuming that this constant is positive. So 3 alpha minus 1 is greater than 0. If it isn't, well, then you can look at other regimes. All right, so that's what sigma and omega is doing. And now you close the loop, you want to compare this with this over here. And so how are these going to match? Well, first of all, if I want to take the inverse of the denominator and for it to match the Green's function, one possibility is that this mu exactly cancels this 0. So we look for the solution where mu equals sigma of 0. Suppose mu was not equal to sigma of 0, well then this is for non-zero mu. So when mu is 0, you would say sigma of 0 has to be 0, which is kind of trivially true if you have particle hole symmetry, but I'm trying to give the more general argument where this also works. So this is an assumption that should be the case. If it isn't, then when you expand the low frequency on the right-hand side, you have to do a different expansion. Okay, so this constant term cancels out. Then this will match with this if this is just the negative of that. So this tells us that alpha minus 1 is equal to minus of 3 alpha minus 1. And if I've done this correctly, that should be alpha is 1/2. Okay, and it satisfies both of these inequalities. Okay, so that's a solution that will work, provided mu is exactly sigma of 0. And you can look at this more carefully, look at other possible cases, other possible values of alpha, and you find that nothing else works. There's no other possible solution except this one that can possibly solve both equations. So you have a result then that g of tau. And now I'll give you the result for general for general mu, and let me get the notation right. I forget the sign here. Yeah, so g of tau is some minus a plus over square root of tau greater than 0, and it turns out to be a minus over square root of tau over tau less than 0. Okay. All right, so now you can also ask about these coefficients here. Now when mu is 0, a plus must equal a minus, and life is simple. But you must, this is the low frequency behavior and more general that will solve at least these sorts of equations. When you look both at positive and negative tau more carefully. So then you can ask what are the values of a plus and a minus. And you can work it out. And it turns out that a plus and a minus are determined. Is some function of u, and you can get it. But a plus over a minus is undetermined. Yeah. In general. Except that mu equals 0, they're equal, but in general it's not. So this is where some subtlety comes in. So you found a one parameter family of solutions at low frequencies. And But you ask yourself, what is the parameter available for you to tune, some dimensionless parameter? The parameter is basically mu in units of u. So you have one UV parameter, which is the chemical potential, which doesn't appear anywhere in the final solution because you assume it cancels with the zero part of the self energy, zero frequency component of the self energy. And in the IR solution at very long times, you also have one free parameter. So there turns out to be quite a remarkable result here. I'll call the Luttinger relation. And it has the flavor of an anomaly or Luttinger relation from the liquid theory. What you find is that so you have one free parameter mu, which you know numerically determines Q, the charge. So Q is expectation value of the equal time correlation function. So that's, you think of that as a UV parameter. So there's a UV number which you can take to be either Q or mu. I'll take it to be Q. In the particle hole symmetric case, Q is 1/2. So Q also goes between 0 and 1. Okay, so you have a UV parameter. So this is the UV constraint. Somebody gives you Q. So you numerically fulfill the equations, you get a solution for a range of values of Q. Then you do the analytic analysis. You get a solution in which Q doesn't appear anywhere, but there's a free parameter, and that's A plus over A minus. So it turns out that these are connected. There's what I'll call a Luttinger relation, which was actually obtained by George Barclay and myself, between A plus A minus, which is the particle hole asymmetry, and Q. And there's an exact relation that we can work out and find in the notes. I won't write it out. It's kind of messy, involves some trigonometric functions and so on. But there's an exact relation between an IR parameter, which is A plus over A minus, and a UV parameter, which is the charge. And the reason I'm calling it a Luttinger relation, well, there's various. One is the Luttinger relation is also in a Fermi liquid, a relation between the UV and the IR. There, it's a relation between the charge, Q, and the size of the Fermi surface. And the Fermi surface is the locus of zero energy excitations. So the Fermi surface is an IR quantity that you can measure in experiment. And once you measure the Fermi surface, you can compute its volume, and then that gives you a connection to Q. So that's the Luttinger relation for an interacting Fermi gas. Here, we don't have any sense of space, but nevertheless, you have a system which is compressible. It can exist at any charge density Q. And it turns out, again, there's a relationship between an IR parameter, which in this case is just the particle hole asymmetry, and Q. And the proof of this actually proceeds very similarly to the proof of Luttinger's theorem. It's intimately connected to the fact that you have a conserved charge and a variable density in a compressible phase with a conserved charge. Okay. All right, so that's the solution, and in numeric, all of these, including the Luttinger relation, agree with numeric, so it all works out very beautifully. So if you plot the spectral function, okay. If you plot the imaginary part of G of omega, there's a minus sign there as a function of omega. So it'll at t equals 0, it'll have this square root behavior, and then it falls off somehow. And there'll be different coefficients here. So this is a plus over some square root of omega, and a minus over the square root of omega. So that's a small omega and a very large omega. Other things can happen that you have to determine numerically. So this is at t equals 0. Okay, so then you can ask what happens at small non-zero temperature. So then you have to solve these equations. Basically you have to make the frequency discrete and put the Q and KMS condition, make things anti-periodic in time, and solve these equations, and then analytically continue to real time. Certainly, when we wrote down these equations in '92 and solved what I've just shown you, that was something I thought would be nice to do, and I had some guesses as to what the solution would look like, but I didn't anticipate that it could be solved exactly. That was done later by George and Barclay, who showed that these equations, in fact, have an analytical solution, even at finite temperature, low temperatures, T is much smaller than U. And what you find then is T much smaller than U, that the G of omega, roughly, one way to write it is that you can put a 1 over square root of T to replace the omega here. And this is a function of just H bar omega over KBT. It's an IR function. And you can actually, well, the fact that we do this was quite clear from the structure of the solution, but you can also get this function exactly. So this function actually forms conformal invariance. So there's an emergent conformal invariance in this theory, and that, which I'm going to discuss very shortly, and that allows you to solve these equations even at non-zero temperatures, T much smaller than U. Okay, so you can look up the form of this function in the notes. I'm going to try to write it out. And basically what it does, it just smooths this thing out on a scale of order KT. So you can think of this as some kind of, again, a lifetime or a dissipative scale that temperature introduces. And that scale at which things smooth out on the zero temperature singularity is just KT over H bar. Now, if you do this, if you had a Fermi liquid, you also have very sharp Fermi surfaces. And then you ask, what's the scale at which the Fermi surface broadens out at finite temperature? Well, you have to look at the self-energy a little more carefully, not this Green's function. You'll find that that scale is determined by the collision time. So the collision time of order, depends on the interaction stress. It's U squared, goes as U squared and temperature squared and so on. So it's a highly non-universal quantity, and which is on an energy scale which is much smaller than temperature, as I said at the very beginning of the lecture. Here, however, the characteristic time where things broaden out is just KT. It doesn't depend on U. And that's kind of the universal behavior and this emergent scale of something that's called Planckian scale that emerges for dissipation in this kind of non-Fermi liquid system. Okay. All right, so that's the result. And Barclay and George first obtained it by just looking at the structure of these equations at low frequencies and just noting that there was an emergent conformal invariance. I'm going to give you a related argument due to Keter, which will also show the same thing. Okay, so any questions? So now I'm going to try to set up the path integral for this theory and talk about some of its symmetries, and that's probably all I have time for.
In deriving the analytic solution, do you also ignore the UV mu term, the chemical potential, or even with the mu term, you can still have this analytic solution?
Well, the analytic solution we only have at frequencies much smaller than U. So it's only at this regime that you have a solution. So yeah, that's the only place you have analytic solution. So you assume for this, yes. So for this, what you're assuming is omega is much smaller than U, T is much smaller than U, but omega over T is arbitrary. So in this regime, you have an analytic solution.
I mean, the chemical potential term. Do we ignore this because you said it's very?
So this function depends on the chemical potential. In fact, it more probably depends on Q. So once you know the charge Q, you get A plus over A minus, And this asymmetry is built into the structure of this function. So it's a different function for different Q. So I need to know the charge density, but that's the only UV quantity I need to know.
Sure.
Because Q determines A plus over A minus. Yeah, and the full function for general Q is in the notes. It's a fun looking function. You can look at it. It depends upon another quantity, which is the ratio of A plus over A minus, which in the end turns out in the black hole mapping related to the electric field on the surface of a black hole. And so you just have to find these conformal solutions in the presence of an electric field, which you can work out. Okay, so yeah, we don't know the dependence on mu. Once you express some things in terms of Q, things are simple. But the relationship between Q and mu, that we have to do numerically. That's a highly non-trivial relation. We can only determine numerically. It depends on the full UV structure of the spheres. But amazingly, when you express in terms of Q, you don't have to worry about what mu was. It just disappears. Q is the only UV quantity that is needed to determine the IR structure. And actually, there are also similar things in black holes. In black hole, this is actually there's a relationship which is just Gauss's law. If you want to determine the surface electric field on the horizon of a black hole, all you need to know is the total charge, and Gauss's law will tell you what it is. This is quite analogous to that. All right, so what we want to do is set up a path integral. We're going to go beyond perturbation theory. So we're going to take a path integral of this model, dc of exponential. Okay, I'm going to be really schematic here. You can find all the signs and other things in the notes. Plus u alpha, h gamma delta, c dagger alpha, c beta, c gamma, c delta. And the whole thing has a d tau. Let me separate that actually. That will be important. So there's a single time integral here, and there's this time integral here. Okay, so now I come in and I average the U. And of course, the way to do that is to introduce replicas and carefully take the n goes to 0 limit and so on. I'll skip all of that because in the end, we know we're going to look at replica symmetric solutions. So if we even drop the replica index, don't worry about it, and then do the average over U. So when you do the average over U, you get the square of this operator, basically, which will give you the following. So now it will give you basically a U squared factor here. And the key now is there's 2 times. And you get C dagger alpha, C dagger theta, of tau, C gamma of tau, C delta of tau. And what's the unusual feature here, because of the randomness, this has, C delta of tau prime, C gamma dagger of tau prime, C beta of tau prime, C alpha of tau prime. Okay, it's 2 different times, and nothing depends on tau minus tau prime. So that looks like an infinite range interaction in time, but it isn't, of course. It's a Hamiltonian system with everything local in time, so it's kind of fake. But that's a feature of this thing. It has a bilocal structure in time, but there is no long-range interaction. And we're going to exploit that bilocal structure in looking at this theory, and it's fundamentally connected to the fact that you're averaging over many systems. Okay, and that's okay because the system, or at least for many quantities, is self-averaging. All right, so this particular, the sum of alpha, beta, gamma, delta, this, it turns out, you can simplify immediately into the following. This becomes basically the integral of d tau, no, not d tau is outside. It's sum on alpha, c dagger alpha of tau, c alpha of tau prime to the power 4. So that's really very nice. And I think there's a factor of 1 over n or something. Again, I'll be sloppy about those factors. I suspect there's a 1 over n here. So now this is extremely nice because this quantity here already has a sum over alpha. When I don't have to keep track of every site. I just have to keep track of this quantity right here. Okay, so that's quantity I'm going to define as the Green's function, of course, g of tau prime, but it's now the 2-time Green's function is equal to, without any expectation value, minus 1 over n, c alpha of tau, c dagger alpha of tau prime, but with a sum over alpha. So we can just sum over all the sites, and the path integral, which had n fermion integrals, can be done immediately. All n have the same behavior, and so you get an integral that instead of having n fields, we have order 1 fields. That's what you can do now. All right, so how do you do that? Well, the nicer way to do it now is by what's called the T sigma theory. You first introduce a delta function to impose this. So you write something like this, dc alpha of delta of this thing, d of tau prime plus minus, oh no, there's a minus there, so it's plus, I'm sorry, this is 1 over n, not 1 over temperature. Plus 1 over n, c alpha of tau, c dagger alpha of tau prime, sum on alpha. And then you take this whole object here, exponential c dagger alpha dc alpha d tau, and this thing is basically d tau prime u squared times g to the power 4. So that's something very simple, and we just put that aside. Okay, and now for this object here, I can try to do the fermion, the integral over the C alpha. So the way you do the integral is you introduce another quantity, which we'll call the self-energy, because its saddle point value will be the self-energy. See, notice these Green's functions are all functions of tau minus tau prime. That will turn out to be the solution of the saddle point. But the Green's function here is bilocal. It's a function of 2 times, independent function of 2 times. And that's actually really quite important to the structure of the theory. The fluctuations, anyway. If you want to really fully understand the fluctuations and their structure, then you've got to keep that to account. So you take this delta function and you write it as a d sigma of exponential of sigma times that, whatever is in here, put that in here. And then what do you notice? Well, then the remaining path integral is quadratic in the C's. There's a C alpha, the C times sigma, and then there's a sigma times G. We don't worry about that. And you can do the path integral over the C's to get a trace log. And so when the dust settle, this is what you get, something like dg, d sigma. These are bilocal fields, but there's only 2 of them. So you had an integral over n fermion fields, which are functions of time. you replace that by an integral over two fields, which are function of 2 times. So of course, this is a much smaller space, even though they're bilocal. And so this is all completely exact. And what you get then is you get n out front, you get a trace log of d by d tau, it's mu minus sigma, and you get sigma times g. If you want to write it out, it's d tau prime, sigma of tau prime, g of tau prime tau, and then another term, which will be mod g of tau prime to the power 4. Okay, so this is all exact with the assumption of self-averaging, which can be verified at least in the Largian limit, and no approximation. And we have taken a path integral in n fields and replaced it by the integral over 2 bilocal fields. So because of the n out front, now we can start to take saddle point values and look at fluctuations. Okay. So I see I'm almost out of time. So let me just again schematically show what are some of the things that appear. All right. So we look at if you look at this path integral, maybe it's easier to see this on the path integral right away. You see that these terms just don't have any dependence on time as such. It's just an integral over time and powers of sigma and g. The only place is some non-trivial dependence on time is this term over here. The mu we found at 0 frequency in the saddle point canceled with sigma of 0. So let's assume that also happens at the saddle. The saddle point of this theory will be the old SY equations. So let's assume that happens also. So we can even don't have to worry about the mu. And what about this d by d tau? Oh, that reminds me of something I forgot to say earlier. When we were solving the saddle point equations, we had this term I omega, that's mu minus sigma of omega. And what we found in the end was that sigma of omega, so this quantity turned out to be equal to mu plus some constant times square root of omega. So this mu cancels that. But what about this term? Well, we also throw that out because omega at low frequencies is much smaller than square root of omega. So this was thrown out. So in the end, when we found the saddle point solution, there was a solution to a quantum problem with fermions to begin with, but at low frequencies, the fermionic commutation relations, which was what this I omega term imposes, didn't matter at all. It just disappeared. Okay, so that's kind of also connected, obviously, to the absence of quasi-particles. So if that was the case, here also we can imagine that this goes away. So then we are left with if I can ignore that, then you notice that this path integral has some remarkable symmetries in this limit. If I ignore the term that I thought of that are not important at low frequencies, then very schematically, the path integral has this form, d sigma dg exponential of trace log of just sigma plus dt d tau prime sigma times g plus g to the 4th. And this integral has time reparameterization invariance. And that ultimately is the reason for connections to gravity, because gravity is space-time reparameterization invariance. This at least has time reparameterization invariance. It's a problem in 0 plus 1 dimension, there's no space. So it ends up being related to 2-dimensional gravity because it's in the boundary of a 2-dimensional space-time, where you're relating in the holographic principle 2-dimensional gravity to a quantum system on the boundary. And that quantum system in this case has time reparameterization invariance. So what is the invariance? Unfortunately, I'm out of time, but I'll just tell you what it is. And there's certainly many more details in the notes. And I can also answer questions tomorrow. Where is it? So with all the factors of 2 and hopefully other things, you find that this thing can be, you can find a new set of variables where you have time reparameterization invariance, and then invariance is you take tau is equal to f of sigma. So this is the old time, this is the new time sigma, and g of tau 1, tau 2 is equal to f prime of sigma 1, f prime of sigma 2 minus 1/4 times some g tilde of sigma 1, sigma 2. So this is the Green's function in the old time. This is the Green's function in the new times. They're related by this. And sigma of tau 1, tau 2 is f prime of sigma 1, f prime of sigma 2 minus 3/4 times sigma tilde of sigma 1, sigma 2. So the claim is when you make these change of variables, you rescale the Green's functions in some way, and you take an arbitrary time reparameterization. The new theory, which is in small sigma time, and g tilde and sigma tilde, has the same form. It looks exactly the same. And you can check that with a few more details in the notes. Okay. So that's clearly quite remarkable that there's this huge symmetry to reparameterization prime, but it's an emergent symmetry. It's not present in the full theory, because the moment you put this term in back in, it disappears. So anyway, so there's a beautiful story then of the consequences of time reparameterization invariance, which leads to some low energy effective action about a conformal saddle point, which is the Schwarzian theory. And so that's due to Vitaev and Maldacena and Stanford and others. I have no time to talk about it, but this is the starting point. And this is also the starting point then of explicit connections to gravity in 2 dimensions anyway. Okay, I unfortunately have to stop. Nobody's come in the door yet, but they will be any minute. So until somebody comes in, I can answer questions.
One question about the trace log sigma part.
Yeah.
When I do this time reparameterization symmetry business, this trace log part doesn't get affected? Is it because I've taken out the TT part of it in mu?
Yeah, so there is some details there. It's easier to look at the saddle point equation than the action, but it does get affected, and all these factors have been chosen, so that also works out correctly. Yeah, so there's a measure that you have to probably worry about. Yeah, but it's a little easier to take the derivative of this with respect to g and sigma, and then you get the saddle point equations, and then it's quite easy to see it works.
Okay.
When you take the derivative, you get 1 over sigma. So it's a little easier to see it there. Okay. So one other point I should mention is that you notice that these are functions of 2 times, not function of tau 1 minus tau 2. And I'm kind of using that in this structure here. You could have different rescaling times of those 2. Okay. So this is the path integral over, this large space of bilocal functions in which there's this reparameterization invariance. But whenever you take an expectation value of any physical operator, including the Green's function, its expectation value, the saddle point plus corrections, will be a function only of tau 1 minus tau 2. Okay. And then the consequences of that on time reparameterization invariance are, in fact, a little more subtle, because the saddle point itself that you start from, which is of this form, doesn't have the full time reparameterization invariance. It only has the SL2R invariance. And that leads to the structure of the Schwarzian and so on. but right. Okay, I think I do have to stop because people are walking in.
Okay, thank you very much. See you tomorrow.